we have already discussed the criteria for the divergence of the sequences and series both. So, today we will discuss few example in support of the divergence that criteria where the series diverges. Just like in a sequence, we have some criteria for the divergence of the sequence. In a similar way, here also we have a criteria for divergence of the limit, that if the limit does not exist, what is the criteria for it. Okay. So, let us see the divergence criteria. Let A be a non-empty subset of R and let F is a mapping from A to R, and let C be a cluster point, C have a cluster point of A. Point of A. Okay. Then the criteria says if L belongs to R, then F does not have limit L at C if and only if there exists a sequence x n, if and only if there exists a sequence x n in A, there exists a sequence x n in A with x n different from C for all n belongs to the set of natural numbers, such that the sequence x n converges to C, but the corresponding images, but the sequence of f x n means corresponding images f of n, the sequence of corresponding images does not converge to L. So, this is the criteria for the divergence. Limit of the function f x when x tends to is not equal to L, it means this will exist. Okay. Now, let us see few example where the sequence of the function or the limit of the function does not exist, which are very interesting examples and used very used frequently in further study. So, first is the limit of this, obviously the limit x tends to 0, signum of x does not exist. It means what? First, the signum, what is the signum of this? Signum function means it is basically sign of the function. So, when x is positive, the value will be 1. When x is 0, the sign of this we consider just a 0. When x is negative, we put it to be minus 1. So, this is the signum function. That is, the function is obviously this is our line. So, when this 0, when x is 0, the function is 1, x is negative, function is minus 1, and at the point 0 we take to be 0. The limit of this signum function when x approaches to 0 does not exist. So, when we approach from the left hand side or we approach from the right hand side, limit will not come out to be the same. Okay. In fact, before this I should prove that whenever the limit of the function f x exists, the limit will be unique, that I will show just after this. So, here the limit will not unique. Let us see why. It means, if I take a sequence x n which goes to 0, but the corresponding function sigma x n does not go to that 0. So, let us choose the sequence x n as minus 1 to the power n. Obviously, this sequence will go to 0 as n tends to infinity. What is the signum of this sequence x n? The signum of this sequence x n, when n is obviously even, it is positive, when n is odd, it is negative, and when so with positive and even number, it is a positive value plus 1, when n is negative, it is a negative value. Okay. With 1 we want minus 1 plus 1. So, basically it is the same as this, that is when n is even you are getting plus 1, when n is odd you are getting minus 1, and this limit we get it. So, for all n belongs to n. Now, limit of this it does not exist, because it varies. When n tends to infinity, it goes to 1 as well as minus 1, when n sequence approach towards the even, when n is odd. So, there are the terms of the sequence which goes to plus 1 even, minus 1 odd. So, nearby this 0 interval, there is a variation of 2, and variation of 2, it cannot be less than epsilon, because we want this thing to be less than epsilon. I choose epsilon to be half. How the variation can be less than half, when the variation is from minus 1 to plus 1, there exactly 2. Okay. So, this limit does not exist, therefore, similarly, another example if I take, suppose I take limit of this x tends to 0, sin of 1 by x does not exist in R. Again, sine function, if I look the sine function, the graph of the sine function is something like this. This is 0, it go plus 1 and minus 1 maximum. So, we can get this thing, this is like this and something like that, then coming from here and similarly here, but as soon as 0 it fluctuates it fluctuates too much, and basically you are getting this thing like this and so on like this, something like means nearby 0 it jumps, keep on jumping, going up and down like this. So, we get the fluctuation, and the fluctuation very thicky around the point 0. We are claiming this limit does not exist. It means, along the two different path, if the limit of the sequence has different value and both the paths tending to 0, then obviously the limit will not exist. So, let us take the limit x n, choose x n to be 1 by n pi, and suppose another sequence by n, if I take 1 by pi by 2 plus 2 n pi. Now, both the things are tending to 0. This is also tending to 0. This is also tending to 0 as n tends to infinity. So, these sequences are converging towards 0, that is mod of x n minus 0 is less than delta. Now, for this sequence, what is the f of x n? If I take f of x n, f x is sin 1 by x. So, what will be the f of x n? F of x n is 0, because when x n is 1 upon n pi, the corresponding sine of n pi and sine integral multiple of pi is 0, while f of by n, this is sine of 2 n pi plus pi by 2, that is always sine pi by 2. So, this will be 1. So, it means the along one point it is 0, sequence along another point the limit of this is 1. So, it does not exist. Therefore, limit of this does not exist. Okay. Now, here as I told that we are assuming the limit is unique, is it not? Limit cannot be two. If the limit of the function exists, it will be unique. So, let us prove that result is and all these exercise which we have depends on this only. Okay. So, this we should prove it earlier, but however, if f is a mapping from A to R, and if C is the crystal point of A, and if C is the cluster point of A, then f can have only one limit at C. We cannot have the two limits. So, proof is, again we will prove by contradiction. Suppose there are two limits, okay. Then finally, we will see that these two limits are not different, they are identical. So, let the f x of this when x tends to C is, suppose let this limit be L and L dash, okay, L and L dash, suppose this is. So, limit of this f x is L when x tends to C, limit of f x when x tends to C is also L dash. Okay. So, apply the definition now. So, for a given epsilon greater than 0, there exists at delta 1 depending on epsilon such that if x belongs to A and 0 is less than mod x minus C less than delta, then delta 1, then mod of f x minus L, let it be epsilon by 2 here, okay. Delta 1 it depends on epsilon by 2, suppose f x minus L is less than epsilon by 2, okay, for all x this. Similarly, here for the same epsilon greater than 0, there exists at delta 2 which depends on epsilon by 2 such that if x belongs to A and x lying between x minus C less than delta 2, okay, then mod of f x minus L is less than L dash is less than epsilon by 2 for all such. Okay. Now, consider mod L minus L. Consider delta to be the infimum of delta 1 and delta 2. So, if I choose replace delta 1 by delta, then this result will also hold. If I choose delta 2 by delta, again this result will hold. So, now consider mod of L minus L dash. Now, this is less than equal to, add and subtract this. So, we can write f x minus L plus f x minus L dash, but f x minus L is less than epsilon L. So, for all x belongs to A and 0 less than x minus C less than delta, this is also less than epsilon L by 2, this is also less than, that is this lesser when this result is. Okay. So, what it shows that this implies L is equal to L, because epsilon is arbitrary small. So, we can get L equal to L, that is the limit will be unique. So, if a functional value f x when x tends to C has a two different limit along the two different path which are approaching to C, then the function will not have a limit at that point. So, that is what, and then such a case we say it is a diverging function diverges at x C. Okay? That is okay. Because diverge does not mean that function limit of this must go to infinity only. It is also one of the criteria when the limit of the function f x when x tends to C is say infinity, it means the function itself is not defined at infinity at the point, okay, and the limit is coming to be infinite. So, it is not finite, but even if it is finite and different, we having different value at a different along the different path, still we say then we say the function f x does not have a limit at x equal to C. So, that is the criteria for this. Okay. Now, this we have discussed. Now, there are few more results over the limits, and that we have seen in parallel to, this will be parallel to our the theorems as we have discussed in case of sequences. Okay. So, before that let us see the definition of the boundedness. boundedness. Let A is a non-empty subset of R, and let F is a mapping from A to R, and let C be a cluster point, of A, be a cluster point of A, C be a cluster point A. We say F is bounded on a neighborhood of C, bounded on a neighborhood of C if there exists and if bounded on a neighborhood, if there exists a delta neighborhood of C, that is B delta C, delta neighborhood of C, and a constant capital M greater than 0, such that mod of f x is less than or equal to m for all x belonging to A intersection V delta C. If this is true, then we say the function f x is a bounded function, is bounded in the neighborhood of C, Okay. If the function has a limit, then it will always be bounded. Okay. So, the result is if A, which is non-empty subset of R, and f is a mapping from A to R, and let has a limit at C, belongs to R, then the function f is bounded on some neighborhood of C, is bounded on some neighborhood of C. Let us see the proof of this result. So, if the limit of the function f exists, then the function f must be bounded in some neighborhood of C. Okay. So, suppose f is the limit, if L is the limit of f x when x tends to C, this is given. Okay. So, let us by definition, so for a given epsilon I choose epsilon to be 1, for a given epsilon greater than 0, because it is already get 0, there exists a delta which will depend on epsilon positive, such that 0, if 0 is less than mod x minus C less than delta, then by definition mod of f x minus L is less than 1. Now, from here can you not say the mod of f x is less than mod L plus 1? Okay. So, I choose m to be, so here m can be chosen as mod L plus 1, then for all x in the neighborhood of this it is there. In case if C also belongs to A, then what we do is we can take m to be the supremum value of mod f c and this bond. So, if I choose this, then all this function f x will satisfy this condition for all x in some neighborhood of C. That is intersection A. Okay. So, this will prove that. Okay, thank you very much. This is we will point in R, which is say a cluster point of A, and the function f is defined on this interval A, as on this set A, which is subset of R. Then we say the function f is bounded in the neighborhood of a point C, means if there exists a neighborhood, delta neighborhood of B delta C, and a constant m such that the values of the function f x for x belonging to this v delta x is less than equal to m. Then we say the function f is bounded over a neighborhood around the point C. And one more result which we have seen, that if the limit of the function exists, if limit of the function f x when x tends to C exist as a limit, then f is bounded on some neighborhood of C. This also we have seen the result. So, these two things, boundedness of the function and this. Now, this result we have proved only one side. If the limit exists at the point C, that a limit of the f x when x tends to C exists, then only we can say function is a bounded function. What about the converse part? The converse means if f is a bounded function on some neighborhood of a point C, can you say the function has a limit at C? The answer is no. So, the converse of this may not be true always. That is, if f is a bounded function on some neighborhood of C, then limit of this function f x when x tends to C may or may not exist. For example, if we take the function f x as signum of, say, signum of x, which we have already discussed signum function, and we have seen that signum x which has a positive value x when value 1 when x is greater than 0, equal to 0 when x is 0, and has a value minus 1 if x is negative. Clear? And this we have seen that this function, the range of this function is bounded. So, in the neighborhood of the 0, it is basically a bounded set, because we can find a constant m is say 1, where all the values of the function clearly f x, which is signum of x, is a bounded function, is bounded in the neighborhood of 0, because we can identify m because we can there exists an m say equal to 1 such that the value of this signum x, it will always remain less than equal to 1 for all x belongs to the delta neighborhood of 0. Okay. But as we have seen, but limit of this function signum of x when x tends to 0 does not exist, because when x tends to 0 from the positive side, the value will come out to be 1, from the negative side the value will come out to be minus 1. So, limit is not unique, or we cannot identify a delta such that the difference between f x minus the number say 0 cannot be less than a smaller value epsilon r. So, it does not exist. So, what we say that the converse of this is not true. However, if we say the function, if it is an unbounded function in some neighborhood of the point C, then obviously function will not have a limit at that point, because when the limit does not exist, there are two possibilities. Either the function is not defined at the point where the limit is required, it means the function goes to infinity or minus infinity when x is approaching to C, or at the point C the function is not at all a finite value. Or second case may be the function has finite values, but at the when limiting value of this has two values or more than two values along a different path. So, in that case the limit will not be unique. So, we say the limit does not exist. So, when we say f is unbounded, it means at the point C the function is not defined at that point. So, it is just like 1 over 1 minus x. At x equal to 1, the function it tends to infinity. In fact, it is not defined, it goes to infinity, unbounded function. So, we can say as a remark or note, if the function f x is not bounded, in the neighborhood, in some neighborhood of say C, then limit of this function f x when x tends to C will not exist, So, that is clear. So, that will be one of the, and that is reason is, for example, if we take the limit of 1 by x when x tends to 0. Suppose I wanted to know whether the limit exists or not. Okay. So, this limit does not exist. Why? Because we have already seen, because if we take a sequence x n say 1 by n, which is belongs to the some delta 1 by n neighborhood or delta neighborhood of 0, say delta is such, so that is the limit, all the terms of the sequence x n belongs to it after certain stage, say delta neighborhood of 0, then this sequence tends to 0 as n tends to infinity. Okay, so, this sequence can, but what about the function? Function f x is giving to be 1 by x. So, what is the functional value? The functional value comes out to be n, which does not go to the smaller quantity, smaller number, all finite number. In fact, it will go to infinity, it goes to infinity as n tends to 1. So, limit does not exist, but this can also be justified from here. Another way of justifying that since 1 by x, this function is unbounded, in the neighborhood of 0, So, limit of this function 1 by x, x tends to 0 does not exist. Okay. So, this is the one way of doing. Now,